Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to be working on a problem where we need to apply a T distribution. Let's begin. So, this is the problem. This is the example I would like to work on with you, okay? So take a look at it, right? So in this case, what we have is a random sample of size 12, so we have 12 observations from a normal distribution, right? And x bar, the sample mean, is 42, and the sample standard deviation is 11.9. Okay, so we have x bar and we have s, meaning sample mean, sample standard deviation, right? Okay, now what we want to do, basically the ultimate goal of the problem, is finding the probability, right, that a sample average based on samples of size 12 is less than 42. So basically what we want is the probability that x bar is less than 42. Make sense? Now again, assumption that we have normality, and furthermore we're going to do this calculation assuming as well that the true mean for that normal is 46. Make sense? Yeah? Okay. So, solution. We want probability that x bar, let me change that, x bar, meaning the sample mean, is less than 46. Okay? That's what we want. Okay? The key to finding that probability will be the following. First, right, remember that if we have a random sample coming from a normal distribution, then x bar also has a normal distribution, right? So let me just remind you, if we have x1, oops, if we have x1, x2 up to xn, from a normal distribution with mean mu and variance sigma squared, then we know that x bar will have a normal distribution too, same mean, but the variance will be affected by the sample size, right? Variance for x bar, that new random variable, is sigma squared divided by n. Remember that? I think that's theorem 7.1 in our textbook. Okay, so That's one of the things that we have here. And remember that here we have that condition, right? That condition is satisfied. We have a random sample of size 12. We have normality, right? We're assuming that those observations are normally distributed. Another thing, note that yes, we're going to be assuming that the true mean mu for those random variables is 46, but we don't have information about sigma squared, right? The population variance, if you will. We don't know that, right? But what we have here is the sample standard deviation, right? So how are we going to make this work? So there's another result. Remember that we talked about that under the same conditions, if you have this, right? Random sample coming from a normal distribution, then we have that n minus 1 times s squared divided by sigma squared has a chi-square distribution with n minus 1 degrees of freedom. Okay? So that's also another theorem that we discussed. I think it is theorem 7.3 from our textbook. Okay? And we have used it before. Okay. So now, the other thing that you have to remember is the definition of a T distribution. Remember that a T distribution is defined as follows. A T distribution is the ratio between a normal 0, 1 and the square root of a chi-square divided by its degrees of freedom. Let me call those guys k, right? So where this guy here, capital Z, represents a normal 0, 1, a standard normal, and W represents a chi-square distribution with k degrees of freedom. So this is the definition of a T distribution, right? It's a ratio between a normal 0, 1 divided by the square root of a chi-square divided by its own degrees of freedom. Okay, and Z and W must be independent. Okay, remember that we obtained the PDF of a T distribution in another video. Okay, anyway, so if you combine 1 and 2, what you're going to have here, right, is this. Note that you could standardize this guy, right? You could do this, x bar minus mu divided by sigma divided by the square root of n, right? Because remember that when you standardize, you don't divide by the variance, you divide by the standard deviation. So the square root of this guy, which is the variance, is this, right? So anyway, now this guy has a normal 0, 1 distribution. Okay? So let me call this guy Z. That's a normal 0, 1. Right? Now, how about, we need a chi-square for the distribution of a T distribution, right? Let's call this guy W, right? And note something interesting. If we define this guy as W, note that the square root, let me copy this guy here, let me do it like this. So in our case, our W has n-1 degrees of freedom, and the definition of a T distribution requires to divide that W by its own degrees of freedom. So in our case, we have to divide by n-1, right? But if you do that, note that this is the same as the square root of 1 divided by n-1 times this, right? So these guys cancel out. So we end up with the square root of s squared divided by sigma squared. But that happens to be the same as just s divided by sigma. Make sense? Okay. So now, let's divide this by this. Note something more. Let me rewrite this guy as follows, just to make the math simpler. Okay? So I'm going to just rewrite this like this. Let me multiply by the square root of n here, can you see that that's the same? Instead of having x bar minus mu divided by sigma, which is divided by the square root of n, that square root of n could go here, right? Multiplying, it's the same, right? Okay, so now we just do this divided by this. So let's do this one. That's our normal 0, 1 divided by the square root of chi squared divided by its own degrees of freedom, which is this. Note that these sigmas will cancel out, so what we end up having here is just square root of n times x bar minus mu, just this, that's the only part that I want, divided by s, right? These guys cancelled out, right? But this is the same as just going to place it in the denominator again. This is the same, it's equivalent, right? Just doing a little bit of algebra. Make sense? But this guy has a T distribution. Okay? Okay, so now we are ready. Note that what we want is the probability that x bar is less than 42. Okay? So let me say that we are ready to solve our problem. We want the probability that x bar is less than 42, right? So, oh, well, what can we do? Well, no problem. What we could do is, I don't know the distribution of x bar. I would if I had sigma squared, but I don't. So we have to estimate it with s squared, but that changes things. Now, instead of dealing with a normal distribution, right, if I knew sigma squared, we know that the distribution of x bar is normal, right? But the problem is we don't have sigma squared. So we have to use the sample variance instead. But if we use the sample variance instead, we have to deal now with a t distribution. So that's the thing. So now we make that guy appear, right? What we do is, oh, this event, x bar less than 42, is equivalent to the probability that x bar minus mu divided by s divided by the square root of n, right, is less than 42 minus mu, right? Mu, we are assuming, is 46, right? It says blah 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 blah. It is claimed that the average is 46, right? And here, where we compute that probability, we go, if that claim is true, find that probability. So we're assuming that mu is 46. So minus 46, sigma squared, we don't have it, but we have the sample standard deviation, S, 11.9. So 11.9, and we know that our sample size is 12. N equals 12. So we need the square root of 12 here. And then our observation is that, guess what? This is the same as trying to find the probability that a t distribution with n minus 1 degrees of freedom, right? Because this guy here has a chi-square distribution with these numbers of that number of degrees of freedom, n minus 1, so that t distribution will have n minus 1 degrees of freedom. Okay, so it's the same as trying to find the probability that a t distribution with 11 degrees of freedom. Another way of writing that down is saying something like this, using a subscript. The distribution with 11 degrees of freedom is less than this guy here. So let me find that number here. 42 minus 46 divided by 11.9 divided by the square root of 12. Okay, so roughly minus 1.1644. Okay. Okay. So now, two ways. Let's try and do this using our table, and then we're going to do it using R. Okay? So using our table. So if you go to page 849, you'll find a table for t distributions. Okay, now again, this guy, that table gives you areas to the right of numbers. Okay, so first, hey, this is a negative number. What do I do here? Oh, no problem. Just remember that t distributions are symmetric. So what you want is the area to the left of negative 1.16, right? Okay. So that would be the same as the area to the right of the positive version of that guy. So that's just first step. Hey, let's use the symmetry of t distributions. That's the same. Probability that t distribution with 11 degrees of freedom is less than negative 1.16 is the same as the probability that t distribution with 11 degrees of freedom is greater than the absolute, well, the absolute value or the positive version of this guy, 1.16. Okay? Okay. Now, we have to find the degrees of freedom that we want. In this case, 11 degrees of freedom, and something as close as possible to 1.16. It turns out that the best that we can do is this guy, right? So what we have here from that table is that the area to the right of 1.363 is 10%, but we want the area to the right of 1.16. So using our table, what we can say is just, you know, that probability that you're interested in is greater than 10%. It's greater than 0.10. Make sense? So let me just say that. So using our table, the best that we can do is saying that this probability that we want, or in other words, this guy, the probability that x bar is less than 42 must be greater than 10%. That's the best that we can do using that table, right? Now, let's do this using R. We know that this probability here is the same as the probability that the t distribution with 11 degrees of freedom is less than negative 1.16 something, right? So there's a function in R that basically gives you, well, it's the CDF. It evaluates the CDF at particular points. For a t distribution, it goes like this, PT. And again, that PT evaluates the CDF of a t distribution at particular points. In this case, we want to evaluate it here, right? So since the CDF is the probability that a random variable is less than or equal to something, that's what we want. And the other parameter, the other argument that you need is degrees of freedom. In our case, we want 11 degrees of freedom. And using R, we know that this guy is exactly, the probability that we want is exactly 13.14, well, 13.44%. Make sense? So let me just point that out here using, using R. What we have is that this probability, the probability that the sample mean is less than 42, is 0.1344 roughly. Okay, so we're done. Let's summarize. So we had this problem where we wanted to say something about x bar, the sample mean, and we had the assumption that our observations came from a normal distribution. We assumed a value for the mean mu. However, we didn't assume anything about the variance sigma squared. So that's why we had to use the information coming from a sample to say something about the standard deviation. So we use the sample standard deviation S. But then that small change well, changes the way we compute test probability. Okay, so what we did is we realized that we could, right, standardized, if you will, x bar, but instead of using sigma, the population, the true variance, well, the true standard deviation sigma, if instead of using that we use the sample standard deviation S, then our calculations are going to change in the sense that instead of using a normal distribution, we're going to be using a T distribution. And we basically derived why that is the case. Okay, using those results that we discussed before, theorem 7.1, theorem 7.3. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.